There are places in the universe where death is not the most frightening possibility. That is the first thing we need to say. Because most of the time, when people imagine cosmic danger, they imagine objects. Asteroids. Supernovae. Black holes. Things that strike matter, crush matter, burn matter, erase matter. We imagine disaster as something happening to bodies. But physics has learned to fear something colder than destruction. It has learned to fear the point where explanation itself begins to fail. There are regimes in the universe where our equations do not merely become difficult to solve. They stop making coherent promises. They return infinities. They predict boundaries to time. They hide information behind horizons. They point toward singularities, toward the first instant of the cosmos, toward scales so small that the distinction between space and geometry may no longer behave the way our theories require. And when that happens, the danger is no longer only physical. It becomes conceptual. Because science is built on a wager. The wager is that reality, however strange, is intelligible. That if we observe carefully enough, measure precisely enough, and think rigorously enough, the universe will answer in lawful form. The universe may be violent. It may be indifferent. It may be hostile to our comfort. But it will still, in some deep sense, make sense. The terrifying thing is not a monster in space. It is the point where explanation loses its footing. Black holes gave us our most dramatic version of that fear. At their center, classical general relativity predicts a singularity, a place where curvature becomes unbounded and the theory ceases to describe the world in any ordinary way. The early universe seems to carry a related wound. Follow our equations back far enough, and the history of space and time itself appears to run into a wall. Push physics down toward the Planck scale, and the smooth spacetime of classical intuition begins to look less like reality and more like a temporary approximation. This documentary is about those edges. Not magical zones. Not places where anything can happen, in the lazy science fiction sense. Not gaps where reason dies. Something more disturbing than that. These are regions and regimes where our current theories, our greatest intellectual achievements, seem to carry us to the border of their own authority. They work magnificently right up to a certain point. And then the language they gave us starts to fracture. That fracture is not proof that the universe is irrational. It may be proof that the universe is deeper than our present descriptions. But for minds like ours, that is frightening enough. Because the universe may not end at the edge of law. But our current speech does. Tonight, we are going to go there carefully. Into black holes. Into singularities. Into the first moments of the cosmos. Into the Planck scale. Into the information paradox. Into the question of whether spacetime itself is fundamental or emergent. Into the possibility that what we call breakdown is not a place on a map, but a boundary in our language and models. We will separate established science from interpretation, and interpretation from speculation. Because if we are going to talk about the point where physics stops speaking clearly, then clarity is the least we owe. And by the end, the universe may feel stranger than when we began. Not because science failed. But because science kept going until it reached a depth where our best theories could no longer carry us whole. The phrase, physics breaks down, sounds dramatic, and that is partly why it is dangerous. It invites the wrong picture. It makes people imagine a hole in reality. A patch of space where nature gives up. A zone where causality dissolves into chaos and law is replaced by magic. But this is not what physicists usually mean, and if we do not get that clear from the beginning, everything that follows will be distorted. When physicists say a theory breaks down, they usually mean something more disciplined and, in a way, more unnerving. They mean that a theory which works astonishingly well across enormous domains is being pushed into a regime where it no longer gives a self-consistent, complete, or physically credible account. The equations may yield infinities. They may require quantities no measurement can define. They may predict singular behavior. They may conflict with another theory that is equally successful elsewhere. They may stop telling us what happens next in any trustworthy sense. That is breakdown. Not nature becoming supernatural. Our present framework reaching its limit. This happens in science for a reason that should inspire humility. Great theories are often great precisely because they do not merely describe safe, ordinary conditions. They describe wide territories of reality with extraordinary success. Newtonian gravity worked brilliantly until relativity revealed its deeper structure. Classical physics worked magnificently until quantum theory exposed a hidden layer beneath it. Each time, breakdown was not the death of knowledge. It was the sign that knowledge had reached its own edge and needed a more profound language. That is the hopeful reading. The darker reading is that some edges cut very close to the foundations of intelligibility itself. What if the problem is not just that we need new equations, but that the concepts we take for granted, space, time, locality, causality, information, even the meaning of a physical state, may not survive unchanged in the deepest regimes of reality? That possibility haunts modern theoretical physics. Inside black holes, general relativity points toward singularities. At the beginning of the universe, classical cosmology appears to hit another singular limit. At the Planck scale, quantum fluctuations of geometry may become too violent for ordinary spacetime to remain meaningful. Around event horizons, the relationship between information, thermodynamics, and geometry becomes so tense that our best theories appear to make incompatible demands. And this is why the subject matters emotionally. Because physics breaks down is frightening for the same reason contradictions are frightening. They do not merely threaten matter. They threaten trust. They suggest that the frameworks by which reality has been made legible to us may themselves be partial, provisional, or context-bound. Now, that does not mean the universe is lawless. Quite the opposite. The history of science strongly suggests that when one framework breaks, a deeper one can often be found. But the moment of fracture still matters. It tells us something profound. It tells us that our best language about the world is not the world itself. This documentary follows that fracture through 16 stages. We begin with the fear of explanation running out. We move through the success and strain of general relativity. We enter black holes and singularities. We follow the crack back to the Big Bang. We descend toward the Planck scale. We ask why infinities so often signal theoretical trouble. We confront horizons, information loss, and the logic of censorship. We examine the search for quantum gravity. We explore competing proposals, strings, loops, holography, bounce cosmologies, emergent spacetime. And finally, we ask what it does to the human mind to inhabit a universe where there may be regions beyond current speech. This is not a documentary about giving up on reason. It is a documentary about what reason discovers when it becomes honest enough to admit where it currently ends. So let us begin where all such journeys begin. With fear. Not fear of impact. Not fear of fire. Fear of the edge of explanation. Human beings can survive a great deal of bad news if the bad news still makes sense. That may be one of the strangest facts about us. We can endure mortality. We can endure grief. We can endure disaster. We can endure the knowledge that stars die, species vanish, civilizations collapse, and that our own planet is not the center of anything. What we struggle with more deeply is the prospect that the world might stop being narratable. That is what makes the edge of explanation so frightening. A world with danger is one thing. A world that ceases to be intelligible is another. All science, at bottom, is a rebellion against that fear. We observe. We compare. We mathematize. We test. We construct theories not merely to predict events, but to secure a sense that reality is lawful enough to be described, linked, and understood. The success of this rebellion has been astonishing. Human beings, primates on a small planet orbiting an ordinary star, have derived equations capable of predicting eclipses, decoding atoms, describing the expansion of the universe, and detecting gravitational waves from black holes colliding billions of light-years away. That success can make intelligibility feel guaranteed. It is not. It is achieved. And it is fragile. Every major revolution in physics has carried an emotional wound inside it. Copernicus displaced us. Darwin naturalized us. Relativity abolished absolute simultaneity. Quantum theory dismantled the old dream of classical certainty. Yet each wound was accompanied by a deeper gain in explanation. The fear surrounding breakdown is different. It is not that the universe turns out to be strange. We have adapted to that. It is that strangeness may eventually reach a point where our current conceptual tools no longer hold together at all. This is why physicists sometimes sound more alarmed by theoretical inconsistency than by cosmic violence. A star exploding is not a crisis for physics. It is an event within physics. But if two of our best theories make incompatible claims in the same domain, the problem is not inside the world alone. It is inside our description of the world. That is a more intimate threat. Because our descriptions are how the universe becomes shareable to minds like ours. Imagine you follow a theory deeper and deeper into extreme conditions. It works beautifully. Every test confirms it. Every calculation aligns with observation. And then, at the point of greatest conceptual importance, it tells you that curvature becomes infinite, time stops, information is lost, or the framework itself can no longer say what exists. That is not just an awkward moment. It is the scientific equivalent of reaching a doorway and discovering your language does not pass through. This fear of the edge of explanation has ancient roots. Myth and religion often placed forbidden regions at the boundaries of the known world, abysses, underworlds, heavenly vaults, sacred mountains. Modern science stripped those boundaries of their supernatural guardians, but it did not eliminate the structure of the fear. It relocated it. Now the forbidden region is not beyond a literal cliff. It is beyond the current reach of a coherent theory. The irony is that physics discovers these regions precisely because it works so well. The better a theory becomes, the more confidently it can be pushed. The more confidently it can be pushed, the more precisely its limits appear. Breakdown is not the first sign of weakness. It is often the last sign of success. That is why black holes and the Big Bang matter so much. They are not famous merely because they are dramatic. They are famous because they are the places where our most powerful theories carry us all the way to the edge, and then appear to fail. There is dignity in that failure. And terror. Because if explanation loses its footing there, then the deepest region of space may not be the one with the most matter or energy, but the one where our current account of what matter, energy, space, and time even are begins to slip. To understand how we got there, we need to appreciate the triumph first. We need to understand how great theories can succeed so completely that their eventual fracture becomes unavoidable. It would be easier if broken theories were merely bad. Then we could discard them without regret. But the theories that reach the edge of their own authority are usually not bad at all. They are masterpieces. They succeed so brilliantly that we trust them into the most extreme regimes imaginable. Their failure matters precisely because their success mattered first. General relativity is one of those masterpieces. Einstein's theory did not merely tweak Newtonian gravity. It reconceived gravity altogether. Massive objects do not pull on one another across empty space in the old sense. Instead, matter and energy curve spacetime, and objects move along the geodesics, the natural paths, of that curved geometry. Out of this idea came a new account of Mercury's orbit, the bending of light, gravitational time dilation, black holes, the expansion of the universe, and gravitational waves. Everywhere we have tested it within its domain, general relativity has performed magnificently. That performance is what gives us the courage to use it in extreme settings. If a theory can describe stars, lensing galaxies, binary pulsars, and cosmic expansion, then it seems reasonable to follow it inward through gravitational collapse and backward toward the early universe. And when we do, it leads us toward singularities. That word will need careful handling later. For now, the point is simple: the equations do not gently fade into uncertainty. They point sharply toward regimes where curvature grows without bound and the theory itself no longer yields a physically acceptable description. Quantum theory tells a similar story. Quantum mechanics and quantum field theory are among the most successful frameworks in the history of science. Their predictions have been tested to astonishing precision. They explain atoms, chemical bonds, semiconductors, lasers, superconductors, particle interactions, and large swaths of modern technology. The Standard Model, built out of quantum fields and symmetries, has survived every experimental challenge of enormous sophistication. Yet when gravity becomes too strong and scales become too small, quantum theory and general relativity stop fitting comfortably together. Each works with terrifying accuracy in its own domain. Together, under the most extreme conditions, they begin to fight. This is what I mean by great theories succeeding too well. They do not collapse in ordinary life. They do not fail in laboratory banality. They take us all the way into the most intense regions of reality, and only there do they reveal that they may not be the final language. That is almost more disturbing than failure in the ordinary sense. Because it means the universe can be legible over immense ranges and still conceal a deeper fracture at the places of greatest significance. Think about what that says about scientific knowledge. We often imagine progress as a smooth ascent toward complete truth. But physics suggests something more dramatic. Theories may be true enough to build civilizations and false enough to break at the foundations. They may be local masterpieces inside a reality still deeper than the conceptual grammar that produced them. This is not a reason for cynicism. It is one of the most beautiful things about science. It means our theories are alive. They are not dogmas. They are instruments sharpened against the world until the world itself reveals where new sharpening must occur. But emotionally, there is a cost. Because when a great theory fails at the edge, it forces us to confront a possibility we would rather avoid, that the ultimate structure of reality may not resemble the categories with which we first learned to speak about it. Space may not be fundamental. Time may not be fundamental. Particles may not be tiny billiard balls. Information may not live where we think it lives. Geometry itself may emerge from something more abstract and relational. That prospect first became impossible to ignore in one of the most famous places in science. The black hole. Black holes occupy a strange territory in the imagination. They are at once among the most established predictions of relativity and among the most conceptually destabilizing objects ever admitted into physical theory. We infer them by their gravitational effects, by accretion physics, by the motion of stars, by jets, by X-rays, by the ripples of gravitational waves, and now by horizon-scale imaging. Black holes are not speculative in the sense that their existence is doubtful. What remains uncertain is what, exactly, happens where relativity pushes us deepest inside them. The classical picture begins simply enough. When enough mass is compressed into a sufficiently small region, gravity wins with terrible efficiency. An event horizon forms, a boundary beyond which escape becomes impossible in the classical theory. From outside, the black hole can be characterized by a remarkably small set of parameters: mass, charge, angular momentum. Much of the detailed complexity of the matter that formed it seems to vanish from the exterior description. This simplicity is part of why black holes are so unnerving. They are regions of immense internal mystery described from outside with almost insulting elegance. Follow the collapse further, and general relativity drives you toward a singularity. Again, we must be careful. This does not necessarily mean there is literally a tiny point of infinite density sitting inside every black hole like a cosmic needle. What it means more responsibly is that the classical description predicts geodesic incompleteness and unbounded curvature. The framework runs into conditions where it can no longer plausibly be treated as final. Singularities, then, are less objects than alarms. They tell us not only that gravity has become extreme, but that general relativity has been pushed into a regime where its own language may no longer apply. Why does this matter so much? Because general relativity is not a toy model. It is one of the deepest and most empirically successful theories ever formulated. If even it becomes insufficient inside black holes, then the black hole is not merely a dangerous object. It is a wound in the reach of classical understanding. And it is not just the singularity that causes trouble. The horizon does too. From outside the black hole, events beyond the horizon are no longer accessible in the ordinary causal sense. This alone already bends the structure of description. Physics likes global stories. It likes complete initial data evolving forward in time. Horizons complicate that. They divide observers. They create regions whose relation to the rest of spacetime is subtle, perspectival, and constrained by causal structure. Add quantum theory to this, and the situation becomes even more severe. Hawking's discovery that black holes radiate thermally transformed them from static graves into thermodynamic objects. They have temperature. They have entropy. They can, in principle, evaporate over vast timescales. And that immediately raises a new kind of breakdown. If the radiation is purely thermal, what happens to the information about what fell in? Is it destroyed? Preserved? Encoded somehow in a form our classical intuitions cannot grasp? That is not a side issue. It is one of the most important signs that ordinary descriptions break under black hole conditions. Classical geometry says one thing. Quantum bookkeeping seems to demand another. The black hole becomes a battlefield where spacetime, thermodynamics, and information are forced into direct confrontation. This is why black holes have become so central to the search for a deeper theory. They are not merely exotic endpoints of stellar collapse. They are theoretical stress tests. Places where gravity becomes so intense that classical spacetime itself may no longer be the right stage on which to speak. Notice the emotional inversion here. The popular imagination fears black holes because they kill. Physics fears them because they reveal the incompleteness of our account of reality. Death is not the deepest issue. Description is. And once you see that, another shift takes place. The most disturbing region of a black hole may not be the place where you are torn apart. It may be the place where our present language is. So what exactly is a singularity, if it is not a simple point-object of doom? We need to slow down there. Because singularities are among the most misunderstood ideas in science, and misunderstanding them makes the entire frontier look more magical than it is. The word singularity has suffered from popularity. It is used in headlines, fiction, futurist rhetoric, casual metaphors, and often as a synonym for the point where weird stuff happens. But in physics, its meaning is more severe and less cinematic. A singularity is not best understood as a thing. It is best understood as a sign. In classical general relativity, singular behavior appears when quantities that describe spacetime curvature become unbounded, or when the spacetime manifold becomes geodesically incomplete in a way that indicates the theory can no longer extend trajectories sensibly. That sounds technical, because it is. But the emotional meaning is straightforward. You have reached a place where the theory stops giving a viable continuation. That is why singularities should be treated less like destinations and more like emergency lights on the dashboard of theory. If your equation produces infinity in a physically central quantity, that does not automatically mean nature contains a literal infinity packaged in a neat little location. Often it means the framework has exceeded its legitimate domain. The theory is telling you, with no particular politeness, that some deeper description is required. This has happened before in science. Classical electrodynamics ran into infinities that later had to be handled through renormalization and deeper quantum structure. Ultraviolet catastrophes signaled the failure of classical assumptions about radiation. Infinities can be clues. They are often evidence not of mystical reality, but of theoretical overreach. The singularity inside a black hole is one such clue. The singularity at the beginning of the universe is another. In both cases, general relativity is powerful enough to carry us almost to the point of origin or collapse, and then it yields a result that seems physically unacceptable if taken as the last word. That does not make the theory useless. It makes it incomplete under those conditions. What makes singularities especially disturbing is that they do not merely mark ignorance. They threaten predictability. Physics usually works by taking a state and evolving it. But if spacetime itself terminates in a singular regime, what does evolve even mean there? What counts as a physical state? What counts as an initial condition? What counts as after? These are not just mathematical questions. They are the grammar of explanation. Singularities therefore touch something very deep in human thought. They are where the idea of a continuous lawful story becomes unstable. We can tolerate strange states. We can tolerate extreme densities. We can tolerate violent curvature. What we resist is the notion that the sequence itself, the carrying forward of law from one stage to another, may not survive intact. Now, it is crucial not to overstate what we know. We do not possess direct observational access to black hole singularities. We do not have a complete quantum gravity theory telling us exactly what replaces them. Perhaps they are resolved into quantum structures. Perhaps geometry dissolves into something discrete. Perhaps inside itself becomes a misleading classical concept. Perhaps the singularity is traded for a bounce, a transition, a different topology, or something more abstract still. The responsible statement is not, the universe contains literal infinities. It is, our current classical description runs into singular behavior, which almost certainly signals the need for deeper theory. And that is already enough to justify dread. Because the terrifying thing is not that somewhere in space there may be a point with infinite density like a magic object. The terrifying thing is that our best classical account of reality carries us to a place where it can no longer speak clearly. That theme echoes beyond black holes. It appears at the origin of the cosmos. It appears in the Planck regime. It appears wherever curvature, energy, and quantum structure may become too entangled for our present frameworks to disentangle them. But before we go to the beginning of the universe, there is another wound inside black hole physics we need to understand. A black hole is not just a place where the interior becomes classically unspeakable. It is also a place the outside can never fully describe in ordinary terms. The event horizon is one of the cruelest ideas in physics because it is so clean. It is not a wall in the usual sense. It is not a shell of matter. It is not a barrier you bounce off. It is a causal boundary. A line in spacetime such that events beyond it cannot send signals to the outside world. That means a black hole does something philosophically violent before you ever reach the singular regime. It partitions reality. From the outside, you can describe the gravitational field, the radiation, the accretion disk, the angular momentum, the electric charge if there is any. But the internal story is not available to you in the way ordinary systems are. There is no simple global description accessible to every observer. Different frames, different causal domains, different information structures all collide here. This is already a kind of breakdown, though not yet a failure of law itself. Ordinary description assumes a level of transparency. Not total transparency, of course, plenty of systems are hard to observe, but enough transparency that in principle the same world is available to shared description if only we had sufficient access. Horizons compromise that dream. They make accessibility itself part of the problem. Now add Hawking radiation and the information paradox, and the problem becomes far deeper. If black holes radiate thermally and evaporate, what happens to the information about everything that crossed the horizon? If it is gone forever, then quantum mechanics seems violated at a foundational level. If it is preserved, then the mechanisms of that preservation may require a relation between interior, exterior, geometry, and entanglement far stranger than classical reasoning allowed. This is where the breakdown of ordinary description becomes severe. The black hole interior and exterior cannot simply be treated as independent classical compartments. The horizon seems too powerful a divider for that, and yet quantum theory resists any story in which information is simply destroyed. Many of the great ideas of modern theoretical physics emerged from trying to repair this fracture. Black hole complementarity. The holographic principle. The ADS/CFT correspondence. More recent work involving quantum extremal surfaces, entanglement islands, and page curve calculations. These are not fringe curiosities. They are attempts to understand how a lawful universe could preserve consistency in situations where ordinary spacetime intuition appears to fail. And notice what that implies. To save coherence, physics may have to give up some of the familiar picture. Space may not be fundamental in the way it seems. Inside and outside may not be independent in the way classical geometry suggests. Information may be represented at boundaries rather than in volume in the way ordinary common sense expects. Entanglement may not merely correlate distant things but help build the geometry we thought was already there. In other words, the region we cannot describe from the outside may be telling us that outside and inside are themselves less fundamental than we assumed. That is not a minor update. It is one of the deepest conceptual destabilizations in modern science. The black hole teaches a brutal lesson. Our intuitive way of describing regions of space may fail exactly where gravity and quantum structure matter most. The horizon is not only a physical boundary. It is a boundary in the classical imagination. And if that were the only place this happened, black holes would still be enough to haunt physics for centuries. But the universe doubles the wound. Because when we follow general relativity backward instead of inward, the entire cosmos seems to lead toward another place where physics stops speaking clearly. The beginning. There is a common picture of the Big Bang that refuses to die. An explosion in pre-existing emptiness. Matter blasted outward from a point. Debris filling a larger and larger external space. It is vivid. It is intuitive. And it is wrong. The Big Bang, in modern cosmology, is not best understood as an explosion into space. It is the hot, dense early state of spacetime itself. Space was not sitting there waiting to be filled. The geometry of the universe was evolving. Everywhere was involved. That clarification matters because it prepares us for the deeper problem. If you take classical general relativity and the observed expansion of the universe seriously, and you evolve the cosmos backward, densities and temperatures rise. Curvature rises. The scale factor shrinks. Eventually, in the classical description, you approach a singular limit. This is often called the Big Bang singularity. And here we must be as careful as we were with black holes. The responsible meaning is not that we have observed a literal mathematical point from which all things exploded. It means that classical spacetime, extrapolated backward, appears to reach a regime where the theory ceases to provide a coherent account. The beginning of the universe is therefore not only a cosmological mystery. It is a fracture in theory. That is chilling for a simple reason. The beginning is not one event among many. It is the context for every later event. If our best classical theory stops speaking clearly there, then the whole story of cosmic origin begins with a limit in description. And yet physics has extracted immense knowledge from the early universe despite this limit. The cosmic microwave background, primordial nucleosynthesis, large-scale structure, inflationary fits, the thermal history of matter and radiation, all of this tells us that the hot, dense early universe is not speculative fiction. It is a robust scientific achievement. We can describe the universe with extraordinary confidence back to fractions of a second after the earliest moments. But not all the way. Push far enough, and the fracture appears. This matters emotionally because it touches a deep human instinct. We want beginnings to be crisp. We want first causes. We want a first room behind which we can ask what came before. But if the beginning of the universe is also the point where classical time and space themselves lose clear meaning, then the ordinary grammar of before may become unstable. And that is where cosmology becomes more than astronomy. It becomes a confrontation between human intuition and the architecture of description. The Big Bang singularity is not frightening because it is physically hot. It is frightening because it marks a region where our present account of time, geometry, and causality cannot be trusted as final. The universe begins, in our current frameworks, with a warning label. This is why quantum gravity is not a luxury problem. We do not seek it merely to polish elegance. We seek it because without it, the origin of the universe remains bordered by a place where our best classical language fails. And the more we examine that failure, the more a new scale begins to dominate the conversation. A scale not of galaxies or stars, but of such tiny distances and such short intervals that spacetime itself may no longer remain smooth. The Planck scale. The Planck scale is one of those phrases that can sound ceremonial if you first hear it too quickly. But it marks something very real in theoretical thought. By combining the constants of gravity, quantum mechanics, and relativity, physicists can construct natural scales of length, time, mass, and energy. The Planck length is unimaginably small, about /10⁻⁻35 meters. The Planck time is unimaginably brief, about /10⁻⁻43 seconds. These are not magic numbers. They are signals that at such scales, quantum effects and gravitational effects should become equally important. And that is the problem. General relativity treats spacetime as a smooth manifold. Quantum theory, in its deepest structure, thrives on fluctuations, uncertainty, and discrete quanta of excitation. At everyday scales, and even at many extreme astrophysical ones, we can often keep these domains conceptually separate enough to get by. Near the Planck scale, that separation should fail. Spacetime itself may become subject to quantum uncertainty. Not particles moving through a classical stage. The stage trembling. This is one of the most conceptually destabilizing possibilities in all of physics. It means the smooth continuum we use to define positions, intervals, trajectories, and causality may not survive indefinitely as a fundamental entity. Distances may lose ordinary meaning. Temporal ordering may become fuzzy in ways our current classical language does not handle gracefully. Geometry may have to be replaced by something discrete, algebraic, relational, holographic, or otherwise deeper than the manifold picture we learned from Einstein. Notice how severe this is. It is not merely that matter behaves strangely at small scales. It is that the very background on which we thought matter behaved may no longer be fundamental. This is why the Planck scale is often described as the edge of classical spacetime. It is not a boundary we can simply fly to in a spaceship. It is a regime. A domain of conditions under which our present ways of speaking about where and when are likely inadequate. In practical terms, we cannot currently probe the Planck scale directly with particle accelerators. The energies required are fantastically beyond our technological reach. That does not make the scale arbitrary. It makes it a frontier inferred from the tension between the theories we do possess. And that inference is powerful. Wherever black hole interiors, the earliest moments of cosmology, or ultra-high-energy gravitational phenomena push us toward Planckian conditions, we expect the classical description to fail. This brings us back to the phrase physics breaks down. Near the Planck scale, the terrifying possibility is not that some monster appears in space. It is that the categories of space themselves begin to lose their classical footing. That is hard to think clearly about because all thought happens somewhere, from some perspective, across some duration. The human mind is built to assume spacetime as a given stage. A regime where the stage is no longer fundamentally smooth is not just difficult to model. It is psychologically insulting. It asks us to imagine that the container of all ordinary imagination is itself an emergent approximation. Some proposals take this literally. Loop quantum gravity suggests quantized structures of geometry. String theory replaces point particles with extended objects and often implies additional dimensions and rich dualities. Holographic ideas suggest spacetime volumes may emerge from lower-dimensional information. Other approaches explore causal sets, asymptotic safety, or more radical reconstructions. They disagree profoundly in details, but they share an intuition: the Planck regime is where the classical image of spacetime stops being enough. And that, again, is not irrationality. It is depth. Still, to understand why physicists react so strongly to these failures, we need to discuss a more technical but central point. Why do infinities in equations cause so much alarm? Why not simply accept them as weird features of reality? Infinity is seductive. It sounds ultimate, final, absolute. Bigger than any number, beyond any scale, an exit from the ordinary world of quantities. That is why popular science writing can sometimes make infinities feel mystical, as if reaching one means we have arrived at the raw edge of existence. Physicists are usually less romantic about them. Because in actual practice, infinities often mean your theory is in trouble. That does not mean every appearance of infinity is meaningless. Mathematics uses infinities in disciplined ways constantly. Some physical quantities can diverge in idealized limits that are well understood. But when a supposedly physical prediction gives you infinite density, infinite curvature, or infinities that cannot be controlled through a coherent framework, the usual response is not awe. It is suspicion. Why? Because measurable reality tends not to hand us literal infinities in the naive way troubled equations sometimes do. Instead, infinities often arise when we push a model beyond the regime where its assumptions remain valid. Classical electrodynamics struggled with self-energy divergences. The ultraviolet catastrophe signaled failure in classical radiation theory. Quantum field theory itself requires renormalization to handle infinities in a mathematically disciplined way. In fluid mechanics and idealized models, singularities can reflect breakdown of approximations rather than reality becoming absurd. So when general relativity predicts infinite curvature at a singularity, physicists hear a warning. Not, you have found the metaphysical center of existence. More often, your classical theory has entered a regime where deeper physics is needed. This is one of the reasons singularities are better treated as alarms. They do not speak in a calm tone. They do not politely request replacement. They scream through the equations that some assumption, continuity, classicality, neglect of quantum gravity, or something even deeper, has ceased to be legitimate. Now, it is worth pausing over something subtle. The fact that infinities often signal trouble does not tell us what the correct repair is. A divergence is a diagnosis, not a cure. One broken theory does not automatically imply one particular successor. That is why the frontier remains contested. But the presence of uncontrollable infinities does justify something strong. It justifies refusing to treat the existing framework as complete in that regime. This matters emotionally because infinities attack the trustworthiness of prediction. A finite theory can be wrong in finite ways. It can be corrected, extended, refined. An uncontrolled infinity is more radical. It says the model no longer yields an answer that can even be interpreted in ordinary physical terms. And when that happens at the beginning of the universe or inside black holes, the stakes become existential for the theory itself. Infinities also reveal a deeper philosophical problem. Science works by relating quantities, comparing scales, extracting measurable consequences. Infinity resists this. It is not just large. It is beyond scaling in the usual way. It can hollow out the distinction between the describable and the undefined. That is why physicists often treat it not as the completion of explanation, but as its interruption. The universe, in this view, may not contain literal infinities in the crude sense our broken equations suggest. Instead, our current speech does. That is one of the recurring motifs of this entire documentary. At the deepest edges of law, the universe may remain coherent while our present frameworks cease to be. The breakdown is not necessarily in reality. It is in the adequacy of the description. But description becomes most fragile where horizons and information join the story. Because then the problem is no longer only unbounded curvature. It is the possibility that the very bookkeeping of physical law is in jeopardy. Information is one of those words that sounds casual until physics claims it. In daily life, information means news, messages, facts, records. In physics, the idea is deeper. It concerns the specification of physical states, the correlations between systems, the encoded structure that allows one state to evolve into another without arbitrary erasure of what came before. Quantum theory, in its standard framework, treats this bookkeeping with extraordinary seriousness. Evolution is unitary. Information can become scrambled, hidden in entanglement, practically unrecoverable for ordinary observers, but the underlying theory resists true destruction. Black holes threaten that resistance. Or at least they seem to. Hawking radiation implies that black holes are not eternal. They can evaporate. If the outgoing radiation is purely thermal in the simplest semi-classical picture, then it appears to carry no detailed memory of what formed the hole or what later fell in. If the black hole fully evaporates, what remains? Just thermal noise? If so, then information about the initial state seems lost. This is the black hole information paradox. And it is not just a technical puzzle. It is a crisis of description at the deepest level. Because if information is truly destroyed, then quantum mechanics may need modification under real physical circumstances. But if information is preserved, then the relation between spacetime, horizons, and quantum states must be far stranger than classical reasoning first allowed. Either way, ordinary description breaks. This is why black holes have become such powerful theoretical laboratories. They force us to confront questions we might otherwise postpone forever. Does spacetime geometry contain all the information we think it does? Is locality fundamental? Can the interior of a black hole be thought of independently of the exterior? What is the true meaning of entropy in a gravitational system? Why is black hole entropy proportional to horizon area rather than volume? How can a region that classically hides everything still participate in a lawful global account? These are not decorative mysteries. They touch the foundation of how physical law is organized. The holographic principle emerged from precisely this pressure. If the entropy of a black hole scales with horizon area, perhaps the informational content of a region is not what naive volume counting suggests. Perhaps the deepest description of a spatial volume lives on a lower dimensional boundary. Later developments, especially the ADS/CFT correspondence, gave this intuition astonishing mathematical power in certain settings. Entire gravitational worlds can be dual to non-gravitational theories living on a boundary. Geometry itself begins to look emergent from a more fundamental informational structure. That is a remarkable rescue attempt. And notice again how the rescue works. Not by affirming common sense. By revising it. To preserve the coherence of law, physics may have to tell us that the world is less like a container full of things and more like a relational structure in which geometry, entropy, and information are entangled at a level far deeper than everyday intuition. This is both beautiful and disturbing. Beautiful because it hints at a hidden unity. Disturbing because it means the regions where physics seems to break down may be pointing beyond the very image of reality we thought we were explaining. There is also a more brutal lesson here. Horizons are not just observational inconveniences. They are structural features of description. They divide who can know what. They complicate any attempt at a single classical story. They make it impossible to pretend that the state of the world is always a simple object available from every perspective in the same way. In that sense, breakdown is not only about singularities or infinities. It is about the collapse of ordinary assumptions regarding access, locality, and shared description. That is why physicists fear exposed singularities so much. If horizons hide some breakdown, perhaps the rest of spacetime remains protected. But what if the breakdown were visible? What if explanation failed in a way the universe did not veil? That fear leads us to one of the coldest ideas in gravitational physics: cosmic censorship. There are conjectures in physics that feel less like theorems and more like prayers. Cosmic censorship is one of them. In rough terms, the cosmic censorship conjecture suggests that singularities produced by realistic gravitational collapse are hidden behind horizons. Nature, on this view, does not allow the breakdown of classical predictability to stand exposed in ordinary spacetime where outside observers can see it and be affected by it directly. That is the charitable intuition. There are technical variants: weak cosmic censorship, strong cosmic censorship, each with precise mathematical formulations and complications. The details are subtle. Some results support aspects of the idea in certain contexts. Other analyses and special models reveal cracks, caveats, or counterexamples in idealized settings. The full story is not a neat slogan. But the emotional stakes are very clear. If singularities are always hidden, then perhaps the failures of classical general relativity are quarantined. The outside universe remains, in a meaningful sense, protected from directly witnessing the region where explanation loses its footing. If singularities could be naked, not clothed by a horizon, then the breakdown of the theory would not remain tucked away behind a causal boundary. It would intrude into visible spacetime. Predictability itself could become compromised in ways not safely sealed off. That prospect horrifies physicists for good reason. The power of physical law depends not only on local equations but on well-posed evolution. Give me appropriate initial data, and the laws tell me what happens. Naked singularities threaten that structure. They imply that there may be visible regions in spacetime where the normal relation between data and evolution becomes undefined, incomplete, or unstable. That is not just another strange object. It is a direct attack on the scientific hope that the universe is globally narratable through law. This is why cosmic censorship, even when technically contested, carries such psychological weight. It encodes a desire that the universe be kind enough to hide its own fractures. Not kind in the human sense. Kind in the epistemic sense. Kind enough that breakdown exists only behind boundaries we cannot cross anyway, rather than appearing out in the open where explanation would fail in public. Now, we should resist turning this into melodrama. There is no confirmed astronomical observation of a naked singularity. Cosmic censorship has not been overthrown by data. But the fact that physicists worry about it at all tells us something profound about what breakdown means. The worst fear is not simply that extreme gravity exists. It is that the limits of our theories might become exposed without protective structure. This is a recurring pattern. Horizons, singularities, and Planckian regimes all teach the same lesson in different ways. Physics remains powerful right up to its edges, but the edges matter because they tell us where our present coherence could be lost. And yet there is a kind of dignity in this. Even as it approaches its own breakdown, physics does not become useless. It becomes sharper. It identifies the exact location of the fracture. It names the conditions. It formulates the problem. It tells us which assumptions are under stress. That is not failure in the ordinary sense. It is the discipline of a theory honest enough to reveal its own horizon. So where do we go from there? If general relativity and quantum theory together lead us to these fractures, what kind of framework could repair them? This is the search that has defined much of fundamental physics for generations. The search for quantum gravity. Quantum gravity is one of the most famous unfinished phrases in science. People say it often, but the emotional weight can get lost through repetition. So let us say clearly what the search is really about. We possess two extraordinary frameworks. General relativity describes gravity, spacetime, and large-scale structure. Quantum theory describes matter, fields, uncertainty, and microscopic phenomena. Each is spectacularly successful. What we do not yet have is a complete, empirically confirmed framework that describes situations where both are simultaneously indispensable, where spacetime itself may be subject to quantum behavior and where gravity can no longer be treated as a mere classical background. That missing framework is what people mean when they talk about quantum gravity. And it is needed because the fractures we have been discussing are not random. They all occur where the classical and quantum descriptions collide: black hole interiors, Hawking evaporation, the earliest universe, Planck scale structure, extreme curvature, information paradoxes. Quantum gravity, if found, would not just be another branch of theoretical refinement. It would be the repair of the deepest tear in our current account of reality. That is why so much intellectual energy has gone into it. But it is also why progress feels so emotionally difficult. The problem is not merely hard. It may require relinquishing some of the most basic features of our ordinary worldview. Continuous spacetime. Locality in the naive classical sense. The distinction between background and object. Perhaps even the status of time as fundamental. Different approaches respond to the challenge differently. Some try to quantize geometry itself. Some try to replace point particles with more fundamental structures. Some treat spacetime as emergent. Some use dualities to show that gravity can be encoded elsewhere. Some build the world out of combinatorial or algebraic relations more basic than space. What unites them is not agreement. It is the conviction that our current fracture is real. Now, the search for quantum gravity is often portrayed as a competition among speculative fantasies. That is unfair in two ways. First, these programs are not arbitrary. They are motivated by specific problems, symmetries, and mathematical pressures. Second, the reason so many approaches exist is not because physicists are careless. It is because the regime we are trying to understand is so deep that multiple roads remain plausible and direct experimental access remains limited. This uncertainty can feel frustrating. It can also feel haunting. Because it means we know enough to identify the wound, but not yet enough to agree on the surgery. Still, quantum gravity is not merely a technical puzzle. It is the attempt to answer one of the most profound questions the human mind has ever asked. What is the world made of when space, time, matter, and law are all pushed beyond the conditions where our current words remain reliable? That is not a small question. And the deeper one goes into it, the more one sees that the repair may come not from adding one more ingredient to reality, but from rethinking what counts as fundamental in the first place. That is why the next part of our journey must examine the major roads beyond the fracture. Not as mythology. As disciplined attempts to make the universe speak again where our current speech fails. If a civilization from another star found its way into our journals and conference halls, it might be astonished by two things at once. How much we know. And how many incompatible ways we currently imagine knowing more. This is the condition of the quantum gravity frontier. String theory, loop quantum gravity, holographic approaches, causal structures, asymptotic safety, emergent geometry programs, bounce cosmologies, these are not identical enterprises. They do not agree on what is fundamental, what is emergent, or even what counts as the right question in some cases. But all of them are, in one way or another, responses to the same fractures. String theory is perhaps the most famous road. In its basic intuition, the fundamental constituents are not zero-dimensional point particles but tiny extended objects, strings, whose modes of vibration correspond to what we perceive as different particles. The framework naturally includes gravity and has generated a vast mathematical landscape involving extra dimensions, dualities, branes, and deep connections between gauge theories and gravity. It has also, through holographic insights, transformed how many physicists think about black holes, entropy, and emergent geometry. The beauty of string theory is hard to deny. The criticism is also familiar: direct empirical confirmation remains elusive. Loop quantum gravity takes a different route. Rather than embedding physics in vibrating strings and extradimensional structure, it attempts to quantize spacetime geometry itself. In this picture, area and volume may come in discrete quanta. Geometry is not infinitely divisible in the classical sense. Spacetime is built from networks and algebraic relations, spin networks evolving into spin foams, rather than from a perfectly smooth continuum. There is a certain severity to this idea that many find attractive. The continuum of general relativity is not abandoned as false everywhere, but it becomes emergent from deeper, granular structure. Other approaches pursue different instincts. Holographic frameworks suggest that bulk geometry may be encoded in lower-dimensional quantum theories. Causal set theory imagines spacetime as fundamentally discrete and ordered by causal relations. Asymptotic safety seeks a consistent ultraviolet completion of gravity through renormalization group behavior. Loop quantum cosmology applies some loop-inspired structure to the early universe and often finds that singularities may be replaced by bounces. There are programs in which spacetime emerges from entanglement, from tensor networks, from quantum error correction structure, or from even more abstract informational relationships. This diversity can seem discouraging. It should also be read as a measure of how deep the problem is. We are not arguing over decorative details. We are arguing over whether the arena of existence is smooth or granular, whether dimensions are fundamental or emergent, whether space is a derived bookkeeping structure, whether time survives at the deepest level, whether gravity is best understood geometrically or relationally or as the shadow of another description entirely. And once again, the emotional stakes are high. Because every one of these roads carries the same unsettling possibility: the familiar world may be a low-energy appearance, not the fundamental layer. Space may be what deeper relations look like from far away. Time may be a semi-classical approximation. Locality may be real enough for ordinary life and derivative in the deep theory. Geometry may not be the bedrock, it may be the foam on top. This is why breakdown feels so disorienting. The repair may not preserve the image. It may preserve the law by transforming the stage on which law is imagined to act. Now, to be disciplined, we must say what these approaches are not. They are not finished truth. They are not all equally supported. They are not experimentally settled. They are not permission to treat the deepest universe as a blank canvas for fantasy. But they are also not arbitrary intellectual games. They are serious efforts to respond where our current theories fail. They are attempts to build continuity across the places where continuity seems presently lost. And if even one of them is pointing in the right direction, then the real region where physics breaks down may not be inside the singularity, in the popular sense at all. It may be the point where we mistakenly insist on classical geometry as fundamental. Which leads to perhaps the most radical idea of all. Maybe space itself is not basic. There are ideas so destabilizing that the first time you hear them, you mistake them for metaphor. Emergent spacetime is one of those ideas. The claim, stated bluntly, is this: what we experience as space, perhaps even spacetime, may not be fundamental. It may arise from deeper degrees of freedom, relations, entanglement structures, or quantum information theoretic organization that do not themselves live in space in the ordinary sense. If that sounds like philosophy, it is only because physics has reached a region where the ordinary image has become too small. The roots of this idea lie in many places. In black hole thermodynamics. In holography. In the strange scaling of entropy with area. In the dualities of string theory. In the suspicion that entanglement is not just a feature of matter placed in space, but something more architecturally central. In approaches where geometry appears to be reconstructed from quantum correlations. In the deep intuition that what we call spacetime may be a coarse-grained description, not the basement level of reality. This matters for our title in a profound way. Because if spacetime is emergent, then the region where physics completely breaks down may not be a place at all. It may be the point at which we are still trying to use geometric language where geometry itself is no longer the right primitive. That is a different kind of terror. It means the breakdown is not merely in equations. It is in ontology. It is in our assumption about what the world is made of. We are used to imagining laws acting on a stage. Things move here. Interact there. Time passes. Geometry exists as the arena of all events. But if geometry is emergent, then the stage is not the final truth. The stage is what deeper order looks like after translation into the terms available to creatures like us. And that means the deepest region of physics may be less like a hidden room behind the wall of spacetime and more like a level of organization from which room, wall, and behind are themselves derived concepts. This is why some physicists speak with such intensity about entanglement, holography, and information. Not because matter has become unreal, but because relations may outrank objects in the hierarchy of explanation. A world can be real and still not be fundamentally built from little solid things in a container. It may be built from lawful structure whose most familiar manifestation happens to be the geometry we inhabit. There is something almost theological in how destabilizing this feels, and yet it is rigorously scientific in motivation. We are not trying to mystify the universe. We are trying to understand why black holes, horizons, entropy, and quantum theory keep pushing us toward the same suspicion, that the classical arena may be emergent rather than ultimate. If that suspicion is correct, then the breakdowns we have been tracing, singularities, Planck scale fractures, horizon paradoxes, are not random disasters. They are boundary effects. Points where the emergent description is being forced to answer questions that only the underlying structure can answer. That is almost comforting. And almost worse. Comforting because it suggests there is a deeper order beneath the fracture. Worse because it suggests the world we know is more provisional than we imagined. It is like discovering that the solid floor under your feet is not fake, but is the visible expression of dynamics you do not naturally perceive. It supports you. It is real enough for life. But it is not the final story of what support is. This is why physics at its frontier becomes so psychologically demanding. It does not merely ask us to accept strange entities. It asks us to downgrade familiar ones. Space. Time. Locality. Geometry. These may remain indispensable at our scales while being derivative at the deepest ones. And now we must do something science rarely does gracefully in public discourse. We must sort the territory. What do we truly know? What are we strongly tempted to believe? What remains interpretive? What is still speculative? Because without that sorting, the edge of explanation turns into a swamp of undisciplined wonder, and that would betray the subject. This is the part where we lower the temperature without lowering the stakes. Because when a subject becomes as conceptually dramatic as breakdown in physics, people begin to slide too quickly from "our current theory fails here" to "anything is possible." That move is emotionally understandable and scientifically irresponsible. So let us separate the layers. What is established? It is established that general relativity and quantum theory are both extraordinarily successful within their respective domains. It is established that black holes exist as astrophysical objects, with event horizons strongly supported by observational evidence and theoretical consistency. It is established that general relativity predicts singular behavior under certain conditions, including gravitational collapse and backward extrapolation of the expanding universe. It is established that Hawking's work and black hole thermodynamics connect gravity, entropy, and quantum effects in ways that force fundamental questions about information. It is established that we do not yet possess a complete experimentally confirmed theory of quantum gravity. It is established that the Planck scale marks a regime where quantum gravitational effects are expected to matter. It is established that infinities appearing in theories often signal the limit of a framework's applicability. What is strongly motivated interpretation? It is strongly motivated that singularities in classical relativity are signs of theoretical incompleteness rather than literal final answers about nature. It is strongly motivated that a deeper theory should preserve the coherence of physical law in regimes where current descriptions fail. It is strongly motivated that black hole evaporation and information questions cannot be treated as superficial puzzles, they are central constraints on any future theory. It is strongly motivated that spacetime may need to be rethought at the deepest levels, perhaps as emergent, quantized, or otherwise non-classical. It is strongly motivated that any successful repair of the fracture will have to reconcile geometry, quantum structure, and information in a much more intimate way than our classical picture allows. What remains debated or speculative? The exact physical fate of singularities remains unknown. The correct theory of quantum gravity remains unknown. The status of cosmic censorship in full generality remains unsettled. String theory is powerful and rich, but not empirically confirmed as the final description of nature. Loop quantum gravity is conceptually compelling to many, but not established as the unique answer. Holographic ideas are extraordinarily fruitful in certain contexts, but the full extension to our cosmological universe remains under development. Bounce cosmologies, emergent spacetime programs, and various quantum gravity proposals remain active research frontiers, not settled doctrine. The deeper philosophical claims often attached to these theories, that time is unreal, that space is an illusion, that the universe is fundamentally information, must be handled with great care. Some are useful shorthand. Some are overstatements. Some are interpretive leaps built on partial evidence. What would be overreach? Saying physics has failed altogether because it contains unsolved problems. Saying singularities prove literal infinities exist in nature. Saying black holes have conclusively destroyed information. Saying one current quantum gravity program has already won. Treating the edge of theory as a blank invitation to fantasy. Using breakdown as a synonym for magic. Reality is stranger and stricter than that. Our current theories do not become worthless at their edges. They become incomplete in specific ways that tell us where the next depth must be sought. That is an extraordinary scientific situation. Not a collapse of knowledge, but knowledge honest enough to map its own boundary. And that honesty has a psychological effect. Because once you understand that there may be regions of the universe where our current speech does not carry, something shifts in how the cosmos feels. It no longer appears merely dangerous. It appears deeper than the language we brought to it. There is a subtle kind of fear that arrives only after education. Children are afraid of the dark because they do not know what is there. Adults can become afraid of the universe because they begin to understand what our knowledge cannot yet carry. That is the psychological shock at the heart of this documentary. It is not merely that there are black holes, singularities, horizons, or Planckian regimes. It is that these regions force a confrontation with a universe that may remain lawful while exceeding the vocabulary through which human beings first learn to trust it. We like the world to have surfaces. We like things to be somewhere. We like time to flow. We like causes to lead to effects in a stable stage we can imagine. We like beginnings to have befores, insides to remain inside, and the language of ordinary objects to scale upward into stars and downward into atoms. Modern physics has spent more than a century breaking those comforts. Relativity destroyed universal simultaneity. Quantum mechanics broke classical determinism and everyday locality. Cosmology removed any privileged center. Black hole theory introduced horizons and singular limits. Quantum gravity hints now threaten the fundamentality of spacetime itself. Each move has made the universe less like a room and more like a structure whose deepest logic is not built for the convenience of mammalian intuition. That is not a flaw in the universe. It is a wound to the human need for legibility. The phrase regions beyond current speech is important here. I do not mean mystical silence. I mean the frontier where our best established conceptual frameworks cease to provide a coherent, settled, common description. We can still calculate. We can still propose. We can still constrain. But the clean continuity between words and world becomes strained. That strain matters psychologically because language is how we inhabit reality together. A theory is not only an equation set. It is a way of rendering the universe discussable. When the theory fractures, the discussable world fractures with it. This is why theoretical physics can feel so emotionally intense even when it concerns scales no human will ever visit. We are not only discovering distant objects. We are discovering the limits of the forms by which the distant becomes thinkable. There is humility in that. There is also a kind of loneliness. Because it reminds us that no matter how powerful science becomes, the human mind may not be entitled to a final picture that feels like common sense scaled up. We may get truth without familiarity. We may get coherence without imagery. We may get equations that work while the metaphors we crave keep dissolving. And yet there is another side to this psychological shock. Wonder. A universe with regions beyond current speech is not a failed universe. It is a universe still capable of exceeding the conceptual nets we have cast into it. That can be maddening. It can also be magnificent. It means the world has not been exhausted by our present categories. It remains, even after all we have learned, more than our current speech can contain. This is where science and existential feeling meet most honestly. Not in fake certainty. Not in mystical surrender. But in disciplined astonishment. We have mapped stars, fields, atoms, galaxies, black holes, expansion, quantum states. And still there are places where our greatest theories begin to fracture. That is not proof of defeat. It is proof that the cosmos remains rich enough to wound our frameworks and call forth better ones. Which brings us to the last step. If there really are regimes where physics, as we currently possess it, breaks down, then what should we finally say about them? What is the deepest truth here? Let us gather everything carefully, because this subject is too easily corrupted by either sensationalism or timidity. There are indeed regions and regimes in the universe where our current theories cease to give a fully coherent account. Inside black hole singularity regimes, general relativity predicts its own limit. Near the beginning of the universe, classical cosmology points toward a fracture in description. At the Planck scale, quantum gravitational effects are expected to become unavoidable, and smooth classical spacetime may no longer remain fundamental. At event horizons, information, geometry, and thermodynamics collide in ways that expose the incompleteness of ordinary description. These are real scientific tensions. They do not mean the universe becomes magical. They do not mean anything goes. They do not mean physics is defeated in some lazy anti-scientific sense. They mean something more serious. They mean our current frameworks are not the final ones. That is the terrifying truth hidden inside the phrase, physics completely breaks down. The breakdown is not usually in nature. It is in the adequacy of our present language about nature. The world continues. The equations fracture. The universe does not have to become irrational for our current speech to lose its footing. That distinction matters. Because once you understand it, the frontier stops looking like a forbidden haunted zone and starts looking like a demand. A demand for deeper law, deeper structure, deeper imagination disciplined by mathematics and evidence. Singularities become less like objects and more like alarms. Infinities become less like revelations and more like warning lights. Horizons become less like special effects and more like structural facts about access and description. And every one of those warning lights points toward the same possibility. The world is deeper than the frameworks that carried us this far. That is not an embarrassment for science. It is the glory of science. A bad enterprise hides its contradictions. A living one uncovers them. General relativity did not fail because it was weak. It failed at singular regimes because it was powerful enough to reach them. Quantum theory did not fail because it was sloppy. It failed to merge cleanly with gravity because it describes microscopic structures so well that the unresolved tension became unavoidable. Modern cosmology did not fail because it was vague. It carried us backward to the earliest moments and showed us exactly where classical reasoning stops being enough. This is the difference between superstition and science. Superstition fills the gap with comfort. Science maps the gap and says, here. Here is where our present understanding ends. Here is where the next theory must begin. And yet there is an existential cost to that honesty. Because we are creatures who want the universe to bottom out in pictures we can hold. A deep place. A first moment. A smallest object. A final stage. A floor under explanation. Physics keeps suggesting that those desires may be more autobiographical than universal. The world may not be built from things but from relations. It may not begin with a clean first instant in the way common sense wants. It may not sustain classical geometry all the way down. It may not preserve the categories of here and there, before and after, inside and outside, in the forms our ordinary language was designed to manage. That is what makes the deepest region of breakdown so unsettling. It may not be a place on a map. It may be the point where our own mode of asking becomes too shallow for what is there. The universe may not end at the edge of law. But our current speech does. And from that edge, a new picture begins to glimmer. Perhaps spacetime is emergent. Perhaps singularities are healed by quantum structure. Perhaps horizons are clues to a deeper informational architecture. Perhaps the beginning of the universe was not a singular point but a transition. Perhaps geometry itself is a coarse-grained appearance of something more fundamental, more relational, more abstract, and more exact than anything in common sense. We do not know. That uncertainty must remain intact. But uncertainty is not emptiness. It is structured by what we have learned. The road beyond current speech is not arbitrary darkness. It is lined with clues: thermodynamics, entanglement, holography, Planckian scales, singular behavior, the success of quantum theory, the triumph and fracture of general relativity, the persistent suspicion that continuity, locality, and geometry may be emergent features rather than eternal truths. This is why the final emotional landing of this documentary is not despair. It is awe sharpened by humility. Where physics breaks down, the universe does not necessarily become absurd. It becomes deeper than the frameworks that carried us there. That is harder to dramatize than a monster. Harder to film than an explosion. Harder to summarize in a headline. But it is, I think, far more profound. The terrifying thing is not that somewhere in space there may be a forbidden region where reason dies. The terrifying thing is that reason can go so far, so successfully, so beautifully, and then discover a depth at which its current form must change. We stand in a universe that is intelligible enough to reveal its own fractures. That may be one of the most astonishing facts we have ever learned. Because it means we have reached a frontier where ignorance is no longer empty. It is articulated, measured, named. A frontier where black holes, the Big Bang, the Planck scale, information paradoxes, and competing quantum gravity proposals all point toward one cold conclusion. Reality is not exhausted by the concepts that first made it comprehensible. And perhaps that is the deepest region of breakdown of all. Not where law ends. Where our confidence that we already know what law must look like finally does.